You open Gmail and never see 90% of the spam that was sent to you. Your phone buzzes. A text message pops up. Before you even open it, something already decided spam or not spam.
That decision happened in milliseconds. Using math you can build yourself. Hi, I am Mahaz, an AI engineer.
Last episode, recommendation systems predicted what you would want to watch next. Today, text classification, how machines read words and sort them into categories without any deep learning. Episode 30, text classification with classical ML. Machine learning models only understand numbers. A house price model gets square footage, bedrooms, location, already numeric. A text message is just words, no numbers anywhere.
So before any model can classify a sentence, we have to turn language into numbers.
That conversion, text to numeric vectors, is called vectorization. Get vectorization right, and even simple classical models perform shockingly well on text.
No transformers, no deep learning needed, just clever counting.
This exact idea powers spam filters, sentiment analysis, and support ticket routing today. Every major email provider still runs some form of this classical pipeline, even in 2026.
Before vectorizing, raw text needs cleaning.
Step 1. Lowercase everything. Free and free should mean the same thing. Step 2. Strip punctuation and numbers that add noise, not meaning. Step 3. Tokenize. Split the sentence into individual words. Step 4. Remove stop words. Words like the, is, and, that carry no classification signal. Step 5. Stemming or lemmatization. Running, runs, and ran all collapse to one root form.
What is left is a short list of meaningful, normalized tokens.
This pipeline runs before every single classical NLP model you will ever build. Stemming is crude and fast, chopping suffixes. Lemmatization is slower, but grammatically correct. NLTK and Spacey both ship ready-made stop-word lists and stemmers, so you rarely build these from scratch. Bag of words, the simplest way to vectorize text. Build a vocabulary, every unique word across all your documents. Then represent each sentence as a row of word counts.
Order does not matter. Grammar does not matter. Only which words appear and how many times.
Free money now becomes a row of mostly zeros, with a 1 under free, money, and now. It throws away word order completely. That is the bag part.
Simple, fast, and still a strong baseline for spam and sentiment tasks.
The catch, with a big vocabulary, most rows are almost entirely zeros. That sparsity costs memory. Scikit-learn's count vectorizer builds this whole table for you automatically from raw sentences. Bag of words has a flaw. Common words dominate the counts. TF-IDF fixes that. Term frequency times inverse document frequency. Term frequency, how often a word appears in this document. Inverse document frequency, how rare that word is across all documents.
A word in every single document, like the, gets an IDF near 0. It gets silenced. A rare, distinctive word in a spam dataset gets a high IDF. It gets amplified.
Multiply the two together, and you get a score that rewards words that are frequent and distinctive. Scikit-learn's TfidfVectorizer computes all of this automatically. You never write the formula by hand. Let's compute it on 2 real sentences. Document 1, free money now. Document 2, meeting scheduled now. Now appears in both documents. Low IDF, it gets downweighted in both rows.
Free and money only appear in document 1. High IDF, high final TF-IDF score.
Document 1 now looks unmistakably spam-shaped to the model, without ever reading it like a human. This is the vector Scikit-learn's TfidfVectorizer builds automatically in 1 line of code.
That's the entire trick. No neural network, just weighted counting done carefully.
Scale this same idea to a vocabulary of 10,000 words, and you have a real spam classifier's input. Naive Bayes, probabilities answer to text classification. It asks, given these words, what is the probability this is spam versus not spam? Bayes' theorem flips that, the probability of the words given the class, times the prior probability of the class.
The naive part, it assumes every word is independent of every other word.
That assumption is technically wrong. Words absolutely depend on each other.
But naive Bayes still works remarkably well on text, and it trains almost instantly.
Multinomial naive Bayes is the standard choice for word count and TF-IDF features. Training means counting word frequencies per class. No gradient descent, no iterations, just counting.
That is why spam filters from the early 2000s already used naive Bayes, decades before deep learning existed. Logistic regression takes a different route.
It learns a weight for every word in the vocabulary, how much that word pushes toward spam or not.
Some of the weighted words, passed through a sigmoid, get a probability between 0 and 1. Unlike naive Bayes, it does not assume word independence. It can learn word interactions through its weights.
In practice, logistic regression with TF-IDF often edges out naive Bayes on larger datasets.
Naive Bayes wins on tiny datasets and blazing speed. Logistic regression wins on accuracy at scale. Logistic regression's weights are also interpretable. You can literally rank which words push towards spam hardest.
For a first classifier on any new text dataset, try both. The fit takes seconds either way.
Evaluating a text classifier.
Accuracy, percent correct overall, but misleading on imbalanced data, like 95% ham, 5% spam. Precision, of everything flagged as spam, how much actually was spam? Recall, of all the real spam, how much did we actually catch?
F1 score, the harmonic mean of precision and recall, one number that balances both.
The confusion matrix shows all four outcomes at once. True positive, true negative, false negative.
For spam filters specifically, false positives, real emails marked as spam, are usually the costlier mistake.
So teams often tune the decision threshold to favor precision over recall on purpose.
In code, this is barely 15 lines.
TfidfVectorizer converts raw text straight into numeric features.
Fit it only on training data. Fitting on test data leaks information and inflates your score.
Then it's the same 3 steps as every model. Fit, predict, evaluate. Swap MultinomialNB for logistic regression in one line to compare both instantly. Wrap it all in a scikit-learn pipeline, and the vectorizer and classifier travel together as one object. If this helped, subscribe. Deploying ML models is next.
Common mistakes. Fitting the vectorizer on the full dataset before splitting, that leaks test data into training. Ignoring class imbalance. A model that always predicts ham can still hit 95% accuracy and be useless.
Removing stop words blindly, not as a stop word in some lists, and removing it can flip sentiment meaning. Judging only by accuracy. Always check precision, recall, and F1 on the minority class.
Skipping engrams. Not good and good mean opposite things, but bag of words alone can't tell them apart.
Overstemming. Chopping words so aggressively that unrelated words collapse into the same meaningless root.
Each of these mistakes quietly inflates your reported score while your real-world performance stays flat.
Quick recap. Preprocessing, lowercase, clean, tokenize, remove stop words, stem. Bag of words, raw counts. TF-IDF, counts weighted by how rare and distinctive a word is. Naive Bayes, fast, probabilistic, assumes word independence. Logistic regression, learns per word weights, usually more accurate at scale.
Evaluate with precision, recall, and F1, never accuracy alone on imbalanced text data.
Together, that's the entire classical NLP toolkit. No transformers required.
Episode 31, Deploying ML Models.
Flask, Fast API, and saving models with Pickle or Joblib. Turning today's classifier into a live API anyone can call. Subscribe so you do not miss it.
Challenge task. Build a spam or sentiment classifier using TF-IDF.
Compare naive Bayes against logistic regression on accuracy and F1 score. Write which model won, and show 3 sentences it got wrong. Solution in the repo. This challenge takes about 20 minutes if your pre-processing pipeline from today is solid.
Post your F1 scores in the comments. I want to see who beat naive Bayes with logistic regression.
Gmail, Twitter, product reviews, support tickets.
All of them running some version of exactly what you just learned.
Bag of words. TF-IDF. Naive Bayes. Logistic Regression.
The classical toolkit behind more real-world text systems than deep learning ever touches. Episode 31, Deploying ML Models, drops next. Subscribe. What's the worst spam message you've ever gotten past your filter? Comment below.
See you in the next one.